I'm here to tell you about the challenges that we face when we have to do risk assessment of particles. In particular, it's nanoparticles I want to tell you about. And nanoparticles are particles that are increasingly used because of the properties that we get when we make materials smaller. These properties enable us to make stronger and lighter weight materials, for instance here as bone implants or as a bicycle, like sporting goods. It also enables us to make stain-resistant surfaces or to be used in medical devices, for example in this case for antimicrobial action. But when we do use all these particles in different consumer products, we also need to do a risk assessment, just like we have to do for regular chemicals. The risk assessment is based on this question: is there a risk for the environment? The way we assess this risk is to compare the effects with the exposure. But before we can do that, we need to know something more about the particles. We need to have a scientific insight that we will deliver in a data package so we can make the effects and exposure assessment and the final risk assessment. This risk assessment procedure is challenged by two things. The first one is that it's a time-consuming process, so it makes it difficult to keep up with innovation, and the other one is that particles are not dissolved. For this, I will use this little hourglass to illustrate the time constraints that we are faced with. Time is running. We already have more than 1,400 products already in the market containing nanomaterials, and they have not been risk assessed. This is because of the second challenge, that particles are not dissolved. And what does that mean? Well, it means that there's a fundamental process called diffusion that is not valid when we look at nanoparticles. This is a problem. So if we just stop the time for a bit by turning the hourglass and take a look at it, then if this was a regular chemical and I had a lot of chemical over here and very little over here, in time there would be a diffusion of the chemical from the high concentration to the low concentration. This does not happen when we look at nanoparticles. These particles over here basically don't care if there's few particles over here. They will not move just because there's few. This is the process of diffusion. And that diffusion doesn't happen is a big problem because the risk assessment procedures that we have in place today are based on this very process, diffusion. Therefore, the fact that particles are not dissolved is a serious challenge to the risk assessment we are doing. To illustrate this, we will take a look at what happens in the lab. Here's an algae test. We have algae that are healthy here, and here we have been killing off the algae population. When we expose algae to nanoparticles, we will see that the particles are surrounding the organism. This is not what we would see if it was a regular chemical. There would be a diffusion of chemical going in to the organism, but it would not be placed like this on top of the organism. Another example here is the algal cell again, with gold particles around the cell. That's what I will call a discrete localization. We have the problem that not only do the particles affect the organism, which is what we want to test, but the organisms do actually also affect the particle. So we have a situation where the test object is actually influencing what we are testing. When we look at Daphnia, which is a little water flea that's used a lot in ecotoxicological research, we see also another way that particles behave that is different from dissolved chemicals. Here the Daphnia has been fed with gold particles, and there's an uptake of the particle over 24 hours, shown here in the digestive tract of the organism. When we transfer them to clean water, we see also that the particles are excreted again. This is not what we would usually see with a dissolved organic chemical. There we would have diffusion in over the organism and distribution all over the organism, and not only here in the digestive tract. We also, in the lab, take closer looks into the organism, into the gut section, to see where do the particles actually move. Do they move into the organisms? So when we do tests in the lab today, it's based on the fact that we do expect a dose-response relationship. This means that the higher concentration we have, the more toxicity we will see. This is based on the notion that everything is truly dissolved. But when we go to the lab, we see that there may be a third axis or another dimension that we are not testing. And it's simply because we do not respect the fact that we are testing particles instead of dissolved chemicals. This gives us a problem in risk assessment because we assume monotonous dose response curves, and this is not what we see when we use the standardized tests. So in order to address this, we do a lot of research here at DTU in trying to solve the equation. What is it that should be on the third axis? Why is it that we have low reproducibility of standard tests used today? This is interesting science and also has huge impact on regulation. But there is a problem that it takes time to do this, and we may be in the situation where we keep asking for more and more data, creating what's called paralysis by analysis, keep asking for more data, and it will take more time to complete a risk assessment. So in order to address this, we suggest that we have to turn around the time and take a look at screening warning signals that can enable us to give decision support to companies and to regulators. One way to do it, we have introduced with the consumer products that are available, is to make a simple color coding for the professional end user, for the consumer, for the environment. Is there a risk of exposure? For the humans and for the environment, is there a risk of things being hazardous? In this way, you can get a fast view on different products and compare the alternatives. So one of the solutions is to guide innovation by using these colors instead of asking for more and more detailed data.